It's on page 179. And now we're going to learn factors of polynomials because we're going to start factoring, and that's what the end of this section, or the end of this chapter is factoring. So let's take some notes. Most of this should be a review, I think. So first of all, when you see the word product, it implies multiplication. So when you hear the word product, it implies that you're multiplying some things together. Okay? X times Y equals the product. Okay? So when you multiply things together, you get a product. We call these things that we multiply together factors. So when you hear the word factors, that's what we're talking about. The things that we're multiplying together in order to get a product. Then you have a factor set. And this is just the set of all of the factors of a number. So pick a number for me, Maggie. All right, well, how about a bigger number? 56. Okay. So we want to do a factor set of 56. That's all the factors, all the things that will multiply to get 56. Okay? So for example, 56 and 1 will multiply to get 56. If I wanted to multiply by 2, I'd have 25 and 3 is 28. 28 and 2. 30, 26. That's not divisible by 3. Is it divisible by 4? Sure is. That'd be 14 and 4. Okay. Let's see, not 5, not 6. Would be 7. 7 and 8. Okay. And then you could have an infinite number, because I'm just giving you integers here, but certainly 103 and 1/2 are both factors of 56, because if you multiply those together, you get 56. So there's an infinite number of answers. Okay, but these things here which multiply to 56 are called factor sets. That's all that you need to know about the factor set. A prime number. Who can tell me what a prime number is? Crystal?
Isn't that when only one thing can go into it or whatever?
It's a number that has exactly 2 whole integer factors, namely 1 and itself. Okay. So if a number only has 2 integer factors, 1 and itself, then it's called prime. Give me an example of a prime number, Austin. 3. 3 is prime. How about another one, Morgan? 7. Good. Let's go around the room. Maggie? 2. Claire?
11.
Good. Eugen? 13. Claire? I'm sorry, Courtney? 5. Good. Courtney Hellman?
1.
No, you guys gotta be careful. 1 is not a prime number. Remember, the definition of a prime number is something that has exactly 2 factors. Well, 1 doesn't have 2 factors, it only has 1, and that's 1. So 1 is not a prime number. Okay, let's try a different one. That's a good mistake to make, though. 17. I don't know how I switched to pink, but Michael Moody. 19. Kayla. 21, 7, and 3. Help her out, KJ. What's that? 23. Good. Okay. We don't have to keep going around. You guys get the idea. They're only divisible by one of themselves. So, notice something here. Notice that here, prime numbers come fairly quick early. 2, 3, then you skip 1, then you skip 1, then you have 2. And notice how after a while, you have to go longer and longer numbers before you find prime. Does everybody see that? If you don't understand what I'm talking about, shake your head like this. Everyone understand what I'm talking about? So back in ancient days, the question came up because the prime numbers, you need more and more numbers before you get to a prime number. Would you one day run out? In other words, is there just a certain number of prime numbers and then you would run out, or is there an infinite number? Who thinks there's an infinite number? Who thinks you would run out someday?
Of what?
Who has no idea what I'm talking about? Okay. Notice here, when you start early counting, the prime numbers come fairly, there's a lot of them. In other words, 2, 3, then you skip 4, then you have 5, skip 6, 7, then you skip 8, 9, 10, you have 11. Notice that as you go on, you get higher, you have to have more and more numbers in between before you get to a prime number. Does everybody see that? So the question that ancient mathematicians faced was this: if you kept going, if we just kept going around the room and around, and we had a year to do it, and just kept picking numbers, would you eventually run out of all the prime numbers, or would there be an infinite number of them? That's the question I'm asking you. So who thinks that you would run out? Raise your hand. And who thinks there's an infinite number? Raise your hand. Yes, there's an infinite number. I'm not going to get into the proof of that today because I don't want to confuse you, but there's an infinite number. Okay, composite. A composite number is a number that's not prime. All numbers are either prime or composite. Okay. Let's see here. Prime factorization. Prime factorization means that we pick a number, for example, 936, and then we factor it into all prime numbers. Okay? So, a good way to start with these is you start with the small prime numbers. What's the smallest prime number? Bethany? 2. And what is half of 936, Bethany? If you need to do it on paper, you can do it on paper. Just take 936 divided by 2. Half of 900 is 450. Half of 30 is 15. 465 plus 3, 468. Okay. Sam. What's 2 times, well, how many times does 2 go into 468?
234.
234. Okay. Sungyoung, how many times does 2 go into 234? 117. Okay. Eugen, I can't divide this one by 2, so what's the next smallest prime number after 2? Is this divisible by 3? What is 117 divided by 3? 39, yes. Okay. Claire, 39 is not divisible by 2. Is this divisible by 3?
Yes.
What is it?
13.
13. Do I have all prime numbers? Yes or no, guys? Do I have all prime numbers? Good. Okay. This is called the prime factorization. In other words, these are all the prime factors of the number we started with, namely 936. So when we factor that, we also use exponents. So for example, how many 2's do I have, Morgan? So I have 2 to the third power. Austin Farrell, how many 3's do I have? So oftentimes our prime factorization, when we simplify it, it's going to be in exponential form. Okay? All right. Any questions on how we do the prime factorization? The GCF, greatest common factor. That's simply the number with the largest value that's a factor of another number. So for example, in the number we just used, 936, what's the greatest common factor of 936? KJ? Do you need me to repeat the question? What is the greatest common factor of 936? We just factored it. These are the factors. What's the greatest? Which one? I can't hear you, I'm sorry. 13, yes. 13 was the greatest common factor of that. Of all the factors, there was 2, 3, and 13. 13 has the highest value. That's greatest common factor. Okay. Least common multiple. The least common multiple of 2 or more integers is the least positive integer having each as a factor when given 2 or more integers. So let's see, let me pick a couple. $72, 108, 126. Okay? And we want to know what is the least common multiple. Okay? So we have to find the factorization. So how are we going to do this? Well, this one here is 2 times 36. 36 is 2 times 18. 18 is 2 times 9. And 9 is 3 times 3. Okay? For 108, it's 2 times 54. 54 is 2 and 25, 27. 27 is 3 and 9. 9 is 3 and 3. That's just 1 3. 126. 2, 50, 63. That's 2. This one's divisible by 3 is 21. 3. That's 3 times 7. Okay? Those are our prime factorizations for the 3 numbers that I picked. What's the greatest common factor, Maggie, of those 3 numbers?
All of them?
Yes.
Would that be 3?
Which one?
3, right?
3. Because you have to, of the factors that are in all of them, 3 is the largest. Notice 7 is only in the one at the end. There's no 7 in those. Okay? What about the least common multiple? To find the least common multiple, take the greatest power of each prime factor. So this is why we have to break them down into exponents. So let's do this. Let's leave it like that. Okay. So this one here was 2 to the third power times 3 squared. That was for the number we had up there. I don't remember what it was. This is 2 squared times 3 to the third power. This one was 2 times 3 squared times 7. Okay? The greatest power of each prime factor. Let me see what else we have. I think those are the only... That's pretty much the only thing that's in this section here. So they're going to go on to factoring tomorrow. But this prime factorization, GCF and LCM are really the only things that are in this section. Before we start doing some problem examples, does anybody have a question?
What's the least common multiple?
The least common multiple is... Well, I read the exact definition on me.
No, like of those
It's the least degree of the common multiple. So what of the common multiples, which are just 3 or 2, which one has the lowest degree? 2. 2 is the LCM. Okay. All right. Let's do some exercises. Let me give you one that we can put down. Let's find the greatest common factor of 20 and 35. So raise your hand when you have the greatest common factor. Anybody? Raise your hand when you have it. What is it? You had it. What is it? 5, right? If I listed these factorizations, this is 5 times 7. Those are both prime. What's the greatest common factor? The greatest number that's in both of them is a 5. Okay, what's the least common multiple? Remember that you have to multiply these to find the total least common multiple. 140, right? Why don't you tell everyone how you got that? How do you get 140?
20 multiplied 7 and 35 multiplied 4.
20 times 5, you said?
Yeah.
And what? 35 times?
4. I know. That is
Huh?
4.
4 what? 35 times 4? And 35 times 4 was?
And that is 7. 20 times 7. I said wrong answer.
20 times 7? Well, of for the LCM, they want the highest one. So yeah, 140 is... Did everybody get the 140 for the least common multiple? Okay. Turn the page. 48. If you're not sure about the least common multiple, watch this, okay? All right. Let's break these down. This is 2 and 24. This is 2 and 12. This is 2 and 6. This is 2 and 3. Everybody see that? Does everybody got that part? Okay. I have 2 to the 4th power times 3. Leave that for a minute. 60 is 2 times 30. 2 times 15. 3 times 5. So this one is 2 squared, 3, 5. If you take the 2 to the 4th power and you multiply it by 3, and you multiply it by 5, notice that I'm taking the 2 to the 4th power. The 3, because this one has the greater exponent between the two. Does everybody see this has the greatest exponent? Shake your head if you know what I'm talking about. The 3's doesn't really matter because they're both to the 1. And then 5 is the only one there. So if I multiply 2 to the 4th times 3 times 5, what do you get? Anybody? 2 to the 4th times 3 times 5. What's 2 to the 4th power? 16. What's 16 times 3 times 5? 240. That is the least common multiple. Does anybody still have a question on least common multiple? No?
Why do you choose only the 5 on there?
Because there is no 5 over here. I use all the prime numbers that I have, and I use the one that has the greatest exponent.
So if there was,
If this was 5 squared, I'd multiply it by 5 squared. If it was whatever number would make that 5 squared.
why aren't you using the other 2 and 3?
What other 2? These 2 over here?
Yeah.
This 3 is the same as this 3. It doesn't matter which one I use. I could not circle this one and use that one. They're both 3 to the 1st power. I'm going to use only one prime number, and then whichever exponent is the highest of that prime number. Do you understand that? So, I don't know what the numbers are, but if I had 2 times 2 times 2 times 3 times 7 times 11, and then I had 2 times 3 times 3 times 11 times 11. If those were my factorizations, and I added those up, I could find what numbers those were. What's my least common multiple? Everybody calculate what your least common multiple of those numbers are. Here I'd use my 2 to the 3rd. Here I'd use my 3 squared. That's my only 7. And it'd be a big long number. You could use your calculator. But the important thing is you know what numbers to use. You don't have to add that all up right now. But that's how you find it. Okay. That's it. You have 2 minutes left. That's all there is in this section, guys. Yeah.
Can you explain the greatest common?
Uh-huh. If you had these numbers here, for the greatest common factor, you want what number is common to both of those. So they both have an 11 in them. Okay? Give me a second to give you the definition again, because I want to read it exactly the way you have it in. The greatest common factor of 2 integers is the greatest integer that is a factor in each. So notice that 11 is in both. So 11 is the greatest common factor. Because these both have it, it's got to be in both, it has to be a number that's in both numbers, and whichever one is greatest. And 11 is the greatest of all those factors. So the GCF is pretty easy to find. There's no calculation. You just have to get down to this prime factorization. And once you do, you see what number's in both, and which number's the greatest that's in both.